topic is, or the presentation is Newton's epistemic triad.
Thank you. Okay, so it's Newton was kind of explicitly and sorry, I lost my train of thought already. Oh, right, that's what I was going to say. So yes, so Newton was kind of explicitly and famously, or almost infamously, anti-hypotheses. So he was kind of famously put passages like this one in his work. So this analysis consists in making experiments and observations and drawing general conclusions from them by induction and admitting of no objections against the conclusions, but such as are taken from experiments or other certain truths. Well, hypotheses are not to be regarded in experimental philosophy. So that one was from Query 31 of the Optics. And this one, which is even more famous or infamous, from the General Scholia to the Principia, he says, I have not as yet been able to deduce from phenomena the reason for these properties of gravity, and I do not feign hypotheses. But whatever is not deduced from the phenomena must be called a hypothesis, and hypotheses, whether metaphysical or physical, or based on occult qualities or mechanical, have no place in experimental philosophy. So the problem is that in every edition of the Principia there are hypotheses. And there are even hypotheses in the Optics. There are even a whole bunch of queries at the end of the Optics which are kind of very speculative in content, and they look an awful lot like hypotheses. And so the presence of hypotheses kind of belies these kinds of statements. You may start to suspect some sort of deception or something. And so I've spent a lot of time sort of trying to make sense of how hypotheses are used. And so the claim that I want to start with today is this. While hypotheses are certainly not the goal of Newton's investigations, they are not an end in themselves, that is, they nonetheless play vital supportive roles in Newton's natural philosophy. So that's the claim that I'm going for. And this is where Howard Stein's work comes in his excellent paper, well, it's a manuscript really, on metaphysics and method in Newton. Stein says this: when Newton says that hypotheses are not to be regarded in or have no place in experimental philosophy, he in no way intends to imply that they have no use in such philosophy. So I take myself as kind of expanding on these kinds of ideas to try and flesh out what those roles actually are in natural philosophy. Stein also talks about Newton as kind of having this multiple vision, by which he means a disciplined ability to entertain conceptions at more than one level. So he says one of the really impressive things about Newton is he's able to kind of think about the metaphysics, the kind of underlying nature of things, but at the same time be talking on a much more phenomenal level about things, and he doesn't let the kind of speculative metaphysics get in the way of trying to say really important, useful things at a different level. And so again, I sort of take myself to be trying to explain some of this sort of work. Okay, so this talk is going to have two parts. I'm going to start by giving you a framework to think about Newton's use of hypotheses and queries and theories in his natural philosophy. I call this an epistemic triad. So I'll give you that framework, and then in the second part I'll give you a case study, Newton's use of hypotheses in his development of his theory of fifths, which is a theory that he puts forward in book 2 of the Optics. Okay, so part 1, we'll start by, so I'll give you an epistemic distinction that Newton works with, the distinction between theories and hypotheses, of speculation and certainty. Then I'll expand on what role Newton takes hypotheses to have in his natural philosophy. Then I'll do a thing where I try and show you that queries and hypotheses are different, that they play different methodological roles in this whole thing. And then by then we'll have built up the framework. So that's what we're doing in this section. Okay, so Newton starts with, there's an epistemic distinction that's really important. It runs through all of Newton's natural philosophy. In his earliest paper, his new theory of light and colours, he said this: for what I shall tell concerning them is not hypothesis, but most rigid consequence, not conjectured by barely inferring 'tis thus, because not otherwise, or because it satisfies all phenomena, but evinced by the mediation of experiments, concluding directly and without any suspicion of doubt. Okay, so there's the conjecture versus certainty, concluding directly and without any suspicion of doubt. Just by the by, I take it that what Newton means by certainty is something like compelled assent. He thinks that kind of the evidence leads you to kind of not to be unable to deny the conclusion. I don't think he means anything stronger than that. And here's another passage from that same book, from that same paper. He says, "I shall not mingle conjectures with certainties." Okay, so I think that what we've got is a distinction here between hypothesis and theory. The terminology here kind of slips around a fair bit. One place in which Newton explicitly does use hypothesis and theory as the two categories that he's distinguishing between is in his letter to Robert Hooke in 1672, where he explicitly uses the term theory to mean what I take him to mean by kind of something that's deduced from experiment and certainly true. But in the Principia, sometimes this is called a theorem or even a problem sometimes, and I think even Principle uses this, captures this meaning for him sometimes, and I think the terms slip around. So yeah, just a caveat there. Okay, so one criterion of being a hypothesis is that it's something that's at best only highly probable, as opposed to criterion of theory, which is that it's certainly true. A hypothesis can also be a conjecture or speculation, so something not deduced from experiment, whereas a theory is always experimental, so it's inferred from observation and experiment. Okay, but there's also sort of another thing going on in this distinction. So here Newton says this, "But to examine how colours may thus be explained hypothetically is besides my purpose. I never intended to show wherein consists the nature and difference of colours, but only to show that de facto they are original and immutable qualities of the rays which exhibit them." He said this in his letter to Hooke. And he also said this, "I knew that the properties which I declared of light were in some measure capable of being explicated, not only by that, but by many other mechanical hypotheses." And so what we're getting here is that hypotheses are kind of often metaphysical. They tell you about the underlying nature of things as opposed to the observable, measurable properties of the thing. So that gives us a third criterion on each side. So something to notice about these criteria for being a hypothesis. This is a disjunctive definition, and so I take it that any proposition that meets at least one of these criteria is a hypothesis on Newton's understanding of the term. Whereas for a theory, theories tend to meet all three of those criteria. In fact, I take it that really theories only meet T1, and T2 and T3 are really corollaries of T1. But I think it's quite useful to kind of spell out all three of those, because I think that Newton really has this kind of experimental foundation to his way of thinking about how we achieve certainty in natural philosophy. Right, so that's what I mean by theory and hypothesis, and I think this is what Newton means as well. All right, and as an example, so for Newton, the theory is something like the claim that white light is a heterogeneous mixture of rays, whereas a hypothesis is something like light is a substance. Okay, so the main kind of point for Newton of natural philosophy seems to be to reason from experiment and observation to certainty, to certain claims about the world. And so these certain claims is a theories, okay? And so we've also now got hypotheses on the table. The idea is that these things are sort of, well, we're still trying to figure out what the connection is between them, but it's clear that hypotheses don't really play a direct role in this trajectory from experiment to certainty. And so now we'll try and flesh out a bit more what they actually do. All right. And Newton says things like this: "Should anyone conjecture from the possibility of a hypothesis to the truth of things, I can't see how they would be able to determine certainty in any science, since numerous other hypotheses always can be invented which shall seem to overcome new difficulties. And for this reason, I place aside improper arguments from the contemplation of hypotheses. So it's claims like this that make us know that Newton doesn't think that hypotheses can have any direct bearing on the kind of certainty that we have for our theories. All right, and then that's an even bigger quote. This one comes from a letter that Newton wrote to Coates in 1713, where I think that he expresses a very similar idea. So he says, one may suppose that bodies may, by some unknown power, be perpetually accelerated and so reject the first law of motion. One may suppose that God can create a penetrable body and so reject the impenetrability of matter. But to admit of such hypotheses in opposition to rational propositions founded upon phenomena by induction is to destroy all arguments taken from phenomena by induction and all principles founded upon such arguments. And therefore, as I regard not hypotheses in explaining the phenomena of nature, so I regard them not in opposition to arguments founded upon phenomena by induction or to principles settled upon such arguments. In arguing for any principle or proposition from phenomena by induction, hypotheses are not to be considered. The argument holds good till some phenomenon can be produced against it. So again, the idea is, if his theory conflicts with your hypothesis, your understanding of, the nature of light, you need to find some experimental evidence to show that the theory is wrong. You can't just rely on refuting it by using your hypothesis. Okay. So now we're going to move on to the role of hypotheses. So in a letter to the Reverend Parties, Newton kind of expanded on how he thought hypotheses should be used. He says this: hypotheses ought to be brought forward only to explicate the properties of things and not to be unlawfully assumed in determining them, except insofar as they may furnish experiments. So one thing is that we're only supposed to use hypotheses to explicate our theories, that is to kind of illustrate them or give them some sort of fill in the bits of it, but we're not supposed to use them to support theories. Just because you have a hypothesis that kind of explains your theory, that's no reason to think that your theory is any truer than otherwise. And also he's telling us that hypotheses might help to reveal new phenomena or properties, so by suggesting new experiments. So those are two roles, I take it, that hypotheses have. And this is another quote from Newton's paper where he actually explains his hypothesis concerning the nature of light. He says, I have observed the heads of some great virtuosos to run much upon hypotheses, as if my discourses wanted a hypothesis to explain them by. And I found that some, when I could not make them take my meaning when I spake of the nature of light and colours abstractedly, have readily apprehended it when I illustrated my discourse by a hypothesis.
I'm sorry, Kristen, I missed, where is this from, this quote?
Oh, this is from his hypothesis paper. It's a big paper that he sent to the Royal Society.
Yeah.
Okay, so some things that we now know about hypotheses. Hypotheses are not true. But that's not even the point of hypotheses. It's actually, for Newton, it's beside the point whether a hypothesis is true or false. You're never supposed to try and test a hypothesis or assume it to be true or anything like that. A false hypothesis could be just as good for him as a true one or whatever. It doesn't really matter. He never once tries to test a hypothesis. Hypotheses are also temporary. So the idea is that if you're going to use a hypothesis, you kind of introduce it for the purposes that you're putting it to suggest an experiment or whatever, and then you take it out, you remove it. It should never be there for the kind of final product, the final justification of your theory. The final product needs to be sort of cleansed of all kind of uncertainties. Okay. So I take it that kind of Newton has kind of given us two different roles. One is that a hypothesis can kind of work in conjunction with a theory somehow to suggest an experiment, and then that experiment will kind of feed back into the certainty. And the other role he's given us is kind of the hypothesis can illustrate somehow. Okay, so now what about queries? Newton uses queries all over the place as well. So it's time to try and figure out what they're doing. Okay, so the first place that Newton uses queries in the kind of ways that I'm thinking about here is in, again, in this letter to Robert Hooke that he wrote in 1672. He says, "I shall now, in the last place, proceed to abstract the difficulties involved in Mr. Hooke's discourse, and without having regard to any hypothesis, consider them in general terms, but they may be reduced to these three queries: whether the unequal refractions made without respect to any inequality of incidence be caused by the different refrangibility of several rays, or by the splitting, breaking, or dissipating of the same ray to diverging parts, whether there be more than two sorts of colours, whether whiteness be a mixture of all colours." So really what Newton is doing here, he's using queries to kind of define the disagreement that he and Hooke are having in empirical terms. And he's sort of using queries then to steer the debate towards the kind of evidence that he thinks is persuasive. But I actually think that this is, he's doing something quite interesting here as well. He's actually using, in this passage, he's actually using Hooke's hypothesis, Hooke's understanding of the nature of light, that white light is homogeneous and it's some sort of pressure or wave, and so on. He's using that to generate a series of crucial tests between his account of light and Hooke's. Well, his account of the elongation of light and Hooke's. And so if you look at something like his first query here, whether the unequal refractions made without respect to any inequality of incidence be caused by the different refrangibility of several rays, or by the splitting, breaking, or dissipating of the same ray into diverging parts, Newton takes this to be a fundamental point of disagreement between Hooke's account of light and his. Newton thinks that the unequal refractions are made by the different refrangibility of different rays. And so he uses this query as the basis from which to describe an experiment that can decide between the two views. And so I think what's going on here is that Hooke's hypothesis provided a temporary platform for Newton to distinguish between the two views. Okay. But then there is a paper where Newton kind of goes into a bit more detail about how to use queries in his work. That he wrote in 1672. He says, "I could wish all objections were suspended, taken from hypotheses or any other heads than these two, of showing the insufficiency of experiments to determine these queries or prove any other parts of my theory, by assigning the flaws and defects of my conclusions drawn from them, or of producing other experiments which directly contradict me." So he thinks that the way to criticize a theory is through the method of queries. You can only criticize a theory by showing either that the query that he has raised cannot be determined experimentally, so that it's not a proper experimental query, or that the query isn't actually a proper test of the theory, or that the query tests the theory and the theory fails that test, or that there's another query that tests the theory and the theory fails that test, so on. So he thinks that the queries kind of provide a crucial way of testing different theories or choosing between theories. Okay, so I think that he thinks that the way that he used the queries in his discussion with Hooke was like this, where he there was a hypothesis and he kind of used that to generate a query. I mean, actually, I think there should be kind of an arrow. I don't know. It's hard to kind of represent it schematically, but anyway, I think that there's sort of the hypothesis is very much feeding into the query there. I think there's also a way that he can use his theories to generate queries as well. So I think that there are at least two different ways that he can go there. Okay, so that was really quick and just trying to sketch this framework, this way that I'm thinking about Newton's theories, hypotheses, and queries. A couple of things to note about it. Firstly, the distinction that I'm thinking about here is epistemic, so it turns on the level of certainty. I don't think that we should be getting too hung up on the labels for these things. As I said before, I think that different things, Newton labels things that fill this position differently in different places slightly. I think the same thing happens with queries. I think that, that in the Principia, the scholia more or less perform the function of queries that queries perform in other places. Hypothesis, I think that he most of the time uses hypothesis in this way, but sometimes they're not kind of labeled explicitly in that way. And the other thing that I think is quite important is that that hypotheses and queries play these important supporting roles in the trajectory from experiment to certainty. And again, part of my project is trying to flesh out what these different supporting roles are, because I think that there are many different ones, and I think they also sort of change and develop over time, and across contexts I think they're slightly different, and so on. So yeah, so that's that. Okay, now we're going to move on to looking at how Newton developed his theory of fits. Okay, so the theory of fits is the theory that Newton developed to explain this phenomenon that's now known as Newton's rings. I think Newton actually kind of discovered rings via Hooke, so the joke's on Hooke yet again. Okay, so what I'm going to do in this section is outline Newton's hypothesis on the nature of light, because that's kind of useful to understand. Then I'm going to explain how he kind of discovered this new phenomenon, this periodicity in light. Then I'm going to show you how he kind of went through various ways of trying to explain this phenomenon there was sort of a shift from pulses and intervals to intervals and so on, and I think this is a way that Newton used his hypothesis to scaffold his theory of fits. And then I'm going to kind of speculate a bit about how we might give a similar account of the way that Newton uses hypotheses to support his queries at the end of the optics. Okay, and so I use the term scaffolding. I kind of mean I'm using roughly an architectural metaphor here. I take it that it's sort of scaffolding in the sense that it's a temporary structure of some kind that's sort of supposed to aid in the building or maintenance of something, and then you can kind of extract it afterwards, ideally. Of course, Alan Shapiro has done a lot of work to point out that that this scaffolding is kind of that the extraction was kind of incomplete in the end, but I'm more interested in what Newton is trying to do rather than maybe what he actually achieved. So we can talk about that in question time if we need to. Okay, so here's the kind of key features of Newton's hypothesis concerning light. So there's an ethereal medium. The ether fills empty spaces, including the pores of solid substances. And it's supposed to be kind of, he's thinking about it a bit like air, except it's, as he says, more subtle and more elastic. Ether vibrates, so it's a thing that carries sounds, sense, and light. And the vibrations, the ethereal vibrations differ in size, and this is what causes kind of different sensations. In fact, Newton relied heavily on this idea in the early 70s when he was developing a theory of vision. He very much thinks that that ethereal vibrations can kind of explain how we come to, how we have sensory experiences and so on. There's also light. So light is different to ether. For Newton, light is a substance that's propagated from lucid bodies and travels through the ether. Despite the fact that everyone's always talking about Newton having a corpuscular hypothesis of light, Newton never really uses the term corpuscle. He tends to talk about it as substance, and then very quickly slips into talking about rays, which we're supposed to understand as substances, but he doesn't come really clean on whether, he doesn't really use the terminology of corpuscles at all here. Right, and so he thinks that these rays are physically heterogeneous, and so they differ in size, shape, and velocity. And so this heterogeneity of the rays, these physical differences between them, combined with their ability to excite vibrations in the ether goes a long way to explaining a lot of different phenomena. And so the light and the ether interact. At least one way in which light and ether interact is that the light warms the ether and the ether presses on the light and so on. So Newton also makes use of these kinds of ideas when he's trying to understand different phenomena. Okay, so Newton discovered a new phenomenon, the phenomenon of periodicity. Let's run through what he did here. Okay, so he started before he carried out this experiment, he grabbed two prisms and pressed them together and noticed that you kind of get these rings, and if you press them really hard together, you kind of get a dark spot in the middle and he realized that the light wasn't kind of reflecting from one surface, it seemed to be passing through. And in order to kind of quantify this phenomena, he grabbed a glass plate and then a glass prism and pressed them together. Not a prism, a lens. The thought being this is a much more kind of regular curved surface, and so he could kind of get regular circles in it. And so he ended up with something that would have looked a bit like this. And he kind of, tried to measure it and do all the things that he always did, count all the circles and look at them in different ways and so on. And what he realized was that there seemed to be a relationship. The size of the rings was proportional to the thickness of the air between the two surfaces. Okay, and so he did things like this where he kind of, examined it from the top, and he actually kind of tried moving, examining it from different angles and so on, and tried to see what the differences were, what happened. And then he kind of looked underneath as well, and again sort of tried to see whether it looked the same and all that. And what he realized was that that you ended up, that if the red was kind of coming through on the top layer, it wasn't appearing down the bottom, if that makes sense. It's hard to do this without using words like reflection and refraction, because that kind of comes slightly later. But that's roughly what he was noticing, was that if the red is kind of coming out, transmitting through the top layer, you couldn't see it below, and so on. And so he sort of tried to very carefully explain this. And another thing that he sort of noticed at this point was that you get repetition in the color. So see how he's got, there's some sort of spectrum here of red to green blue, and then there's another red to green blue, and then we've got another spectrum here, red to blue, purple, red, yellow, and so it was a repeating phenomenon. So the ring, the ring's repeated. Okay, and he also did things like this, where he put different colors, tried just projecting different colored light on it, and he noticed that you didn't get any other colors. That it would just be red if you projected red light, and it would just be yellow if you projected yellow light, and so on. And then, of course, he looked underneath again, and so on. And what he noticed there was that you tended to get, again, some of the light going through and other light going back. And so he said, and so he concluded, and from thence the origin of these rings is manifest, namely that the air between the glasses, according to its various thickness, is disposed in some places to reflect and in others to transmit the light of any one colour, and in the same place to reflect that of one colour where it transmits that of another. Okay, so that was the rings. That was what he had figured out was going on. Okay, so back to this diagram. He wanted to explain how it is that light is being so regularly reflected and refracted in this kind of periodic way. Of course, he'd already offered an explanation for the elongation phenomenon that we get when you transmit light through a prism. And so he tried to use that same, his first idea was to try and use those established properties of light. So variation in refrangibility and variation in color. And refrangibility and color was supposed to be these kind of innate properties that any given ray of light had. But of course, one difference between the elongation of a prism when you put it, the elongation of a spectrum when you put it through a prism. And this is that here you get the repetition of colours. And so he realised that he wasn't going to be able to quite explain it in the same way. Okay, so then that's not showing up as well as I had hoped, but that's, can you see that? Yeah. Okay, yeah. So he started thinking about, so he went back to his, ether and light theory, and he started thinking about, well, if you drop, say, a pebble into a pool of water, it creates ripples or waves or vibrations, as you want to put it. And he started to build a theory of he started to sort of try and construct a theory around that. He thought that there's this thing called a pulse that's happening. So actually the best way I can do it is to show you it this way. Okay, so you've all been in the sea, I'm sure. When you swim out to sea, if you're trying to swim with the current, if you're sort of catching the wave and coming in, you kind of tend to come in quite quickly. If you're trying to swim in against the waves, then it's really, really hard to swim in. Okay, so he thought that there was something like this going on with the ether, so that when the light hits the ether or hits the surface, it sort of begins these vibrations. And the vibrations kind of move sort of more quickly than the light. And if the light tries to travel if the light kind of gets caught up with one of those vibrations, or if it's sort of caught up while the vibration is kind of expanding, it's going to be able to pass through that surface quite quickly. If it kind of gets caught when the vibrations are kind of contracting again, or in this case when the waves are kind of going out again, then it's not going to be able to pass through. It's going to, and so this is the thought that that when it's kind of traveling with the current, as it were, it's going to be transmitted through the surface. If it's traveling against the current, it's going to be reflected back. It's the kind of thing he was thinking about. And this, and the measure that he put forward, or the physical idea, is that this is a pulse. So the pulse is the period or distance between the expansion and contraction of a vibration. And so he was able to kind of quantify this. He decided one pulse, at a distance of one pulse, then you get reflection. 2 pulses, you get transmission. At 3 pulses, you get reflection, and so on. And that's how he thought it went. Oh, and each color, he thought, would excite pulses of different lengths. And this is how you get different colors being transmitted at different times, and you get this repetition, the repeating colors. This is all well and good, but how do you detect a pulse? This is an unobservable phenomenon in an unobservable, undetectable medium, right? It's not very Newtonian to be talking about pulses and so on. But he thought that this was sort of indicated by the regularity of the phenomenon. And so what he did was he ended up operationalizing the concept of a pulse. Okay, so as we saw before, he thought he'd realized quite quickly there was a relationship between the size of the rings and the thickness of the air between the 2 plates. And another thing that he had already realized when he was pressing together, back when he was just pressing together prisms, was that when the 2 surfaces touch, light is transmitted between the 2. In fact, he had this kind of fairly well-developed matter theory at this point too, where that meant that he thought that when you pressed 2 pieces of glass together, the sort of boundary between those 2 pieces disappeared. So as long as the 2 pieces of glass, had the same density, it was as if they were just one piece of glass, and that's why the light would just because there was no surface there. And so he realized that the smallest circle is going to represent the smallest gap required for a reflection to occur. And so then this gave him a thing that he could measure to establish the length of a pulse. Okay, so that ended up being 1 pulse. As Alan Shapiro has shown, the basic idea kind of worked, but the measurements were way off. But he did a good job what he had. Okay, and so then a pulse just became a unit of measurement for him. And he was able to count these things. So reflection occurs when the distance between the two surfaces equals 1, 3, 5, 7, etc. pulses. Transmission occurs when the distance equals 2, 4, 6, 8, etc. pulses. And so I think this is a really interesting case. So what Newton did here was that he took a vague hypothetical concept that was neither observable nor measurable directly, and he attached it to an empirical effect and was then able to clearly define it in a way that he could use. So he operationalized it. Okay, and now I want to run through kind of what he did with it then. So all of this happened very early on, between 1665 and 1666. This is when he was doing all this kind of work. And so in the manuscript of Colours, where he also is first describing the heterogeneity of light, he also is talking about colours. He says, he's also talking about these rings. He says the thickness of the air for one circle was 1/64,000th of an inch, which is the space of the pulse of the vibrating medium. By measuring it since more exactly, I find, yeah, and so here you find that he's really trying to get the measurements right, and you find the whole way through this manuscript that he's crossed out the 64th, I can't even say that word, that word, and he's put in 83,000 of an inch around that. Yeah.
Is the medium the ether or the air, or does it matter?
So the air here, this is just the air between the two surfaces, but the vibrating medium is the ether that's kind of pervading through the air. So yeah. And I just want to point out that's his bracket, not mine. And it just shows that that this is where he's first talking about there being a pulse in a vibrating medium. So this is where this language is coming from. Okay, so in 1675 he wrote his hypothesis, the paper Hypothesis Explaining the Properties of Light, discoursed in my several papers that he sent to the Royal Society. And here he kind of explained what he was thinking about in a lot more detail. So as if the plate be of such thickness that the condensed part of the first wave overtake the ray at the second superficies, it must be reflected there. If double that thickness, that the following rarefied part of the wave, that is the space between that and the next wave, overtake it, there it must be transmitted. If triple the thickness, that the condensed part of the second wave overtake it, there it must be reflected. And so where the plate is 5, 7, or 9 times that thickness, it must be reflected by reason of the third, fourth, or fifth wave overtaking it at the second superficies. But when it is 4, 6, or 8 times that thickness, so that the ray may be overtaken there by the dilated interval of those rays, it shall be transmitted, and so on. Okay, and so on. So he's kind of giving a fairly detailed account that's very much using the idea of there being a vibrating medium. Interestingly, at this point, the language of a pulse has actually dropped out, and he started talking about an interval instead of a pulse. I take it an interval is actually less hypothesis loaded than a pulse, and so I guess he's already starting to kind of slip away from talking about pulses. Okay, 1690, Newton had basically a completed draft of the optics, which he then disbanded and rewrote. But anyway, in 1690 he had, and in these drafts you find he's got a whole lot of propositions, and you find this kind of idea in those. So in this proposition he says the motion excited in pellucid bodies by the impulses of the incident rays of light is a vibrating one, and the vibrations are propagated every way in concentric circles from the points of the incidence through the bodies. So again, there's this kind of vibration, language. We've also got kind of impulses here, but the impulses, as you can see, are related to the rays. So the rays are sort of doing these impulses, not the vibration, not the medium. So that's a bit more complicated. But anyway, and here's another proposition where he says the vibrations excited by the more refrangible rays are shorter than those excited by the less refrangible ones, and upon this difference depends the different reflexibility and different inflexibility of light. One thing that kind of complicates this draft material is that around this time, Newton was starting to try and think about whether you could explain the kind of this periodicity of light in terms of the speed at which the rays of light travel. And so he was sort of playing around with a different way of trying to explain this stuff. He even wrote a letter to Flamsteed and asked him, so he realized that if light does travel at different speeds, then you should be able to observe it in, say, the moons of Jupiter. You should be able to see, say, as the moon kind of just appears around the backside of Jupiter, you should get red light first, say, and then so he asked Flamsteed if he could make these kinds of observations, and Flamsteed replied saying, no, I've never seen anything like that. And so it wasn't long after this that Newton kind of gave up the idea. I'd like to say once and for all, but there is hints of this idea in the queries to the optics as well. So I think it was an idea that he was sort of toying with at different times. But anyway, that's what makes that one a bit more complicated. But anyway, in 1704, he finally published the Optics. And so there we find a very pristine formal theory. Okay, so we've already seen this quote. Part 1 of the Optics, he explains this periodicity phenomenon. And then finally in book 2, part 3, he gives us a proposition explaining it. He says, every ray of light in its passage through any refracting surface is put into a certain transient constitutional state, which in the progress of the ray returns at equal intervals, and disposes that ray at every return to be easily transmitted through the next refracting surface, and between the returns to be easily reflected by it. Which is kind of almost incomprehensible if you didn't know everything that I'd already told you, right? And not surprising. Most people who read this just really had no idea what he was talking about. Because it's been sort of cleansed of all of that language of vibrations and pulses and things, although, yeah, he's not even using, oh yeah, so he's got equal intervals, so he's got intervals in there. So knowing that no one was going to understand this, he then threw in a hypothesis. He says, but what kind of action or disposition this is, whether it consists in a circulating or vibrating motion of the ray or of the medium or anything of something else, I do not here inquire. So he's already putting in a caveat right at the beginning of this discussion saying, look, this is not part of my inquiry, I'm not worried about this, but those that are averse from assenting to any new discoveries, but such as they can explain by a hypothesis, may for the present suppose that as stones, by falling upon water, put the water into an undulating motion, and all bodies by percussion excite vibrations in the air, so the rays of light by impinging on any refracting or reflecting surface excite vibrations in the refracting or reflecting medium or substance, and by exciting them agitate the solid parts of the refracting or reflecting body, and by agitating them cause the body to grow warm or hot. See how he's putting in the whole thing. He's got, the kind of wave motion of the water, and he's even talking about kind of, the light heating the ether somehow and so on. That the vibrations thus excited are propagated in the air for causing sound and move faster than the rays, so as to overtake them. And that when any ray is in that part of the vibration which conspires with its motion, easily breaks through a refracting surface. But when it is in the contrary part of the vibration which impedes its motion, it is easily reflected. And by consequence that every ray is successively disposed to be easily reflected or easily transmitted by every vibration which overtakes it. Okay, so he's just given us kind of the metaphysics, the hypothesis that he's been working with. Right, some things to, yeah, so we've got the vibrations. We've got this explicit description again of what he thinks the mechanism might be. And as soon as that paragraph has happened, he very quickly pulls back again. He says, whether this hypothesis be true or false, I do not here consider. I content myself with the bare discovery that the rays of light are by some cause or other alternatively disposed to be reflected or refracted in many vicissitudes. So he immediately retracts that hypothesis, tries to kind of cleanse it from the formal theory itself, following his own methodology. And then, just to kind of signal that that discussion's done, he then gives us a definition. The returns of the disposition of any ray to be reflected, I would call its fits of easy reflection, and those of its disposition to be transmitted, its fits of easy transmission, and the space it passes between every return and the next, the interval of its fits. So he's just given us some language. And then the rest of this this part of the optics. It's all about him exploring these ideas. Like, this is what he tries to do. He tries to kind of get a better measure of this interval, and that's what all the other propositions in that book are about. Okay, so what's happened here? Ethereal vibrations played two roles with respect to Newton's theory of fits. Firstly, in the optics, Newton introduced the hypothesis to explicate the formal theory. So I take it that was sort of to offer a possibility proof, or even maybe not quite that. It was to kind of make it, it sort of had a pedagogical purpose, I guess. It was to try and help with the uptake of the ideas by other people. So it was kind of to satisfy critics, maybe to satisfy everyone. And importantly, he was really careful to kind of display no epistemic commitment to the hypothesis at this point. But he also uses it in a second way that we don't really see in the pristine formal version of the optics, but because we've got all that manuscript evidence, we can see that this is what was really going on behind the scenes, that he used the hypothesis to posit a physical cause for the observed pattern of coloured rings. So the ethereal pulse was doing this work. So as we saw, he operationalized the pulse, and using it, he kind of gained a unit of measurement that was really able to help him to get a formal theory. And so this offered him, or provided him with a way of formalizing and abstracting the explanation. And so I think it's useful to think about this as scaffolding for the purpose of theory building. Okay, so maybe try and schematize this a little in my epistemic triad. So we had illustration. And so when I first started thinking about this, I thought that this was probably a kind of combining the theory and the hypothesis to experiment. But I actually think it more takes this sort of form, really, even though there's no real explicit query in it. But I think that what happens is that he's got this hypothesis that he then kind of uses to propose a way of, he kind of proposes a new research inquiry, a new investigation or something like this that kind of suggests a whole bunch of experiments that he could carry out that would. So I'm still kind of undecided. I actually think there might be sort of a three-way thing going on in that particular case, but yeah. Okay, and so now I've still got about. Okay, so I take it that hypotheses kind of provide a similar kind of role in Book 3 of the Optics. So at the end of Book 3 of the Optics is supposed to be about interference phenomena, but he kind of runs into this problem quite quickly and can't really explain what's going on. So it's supposed to be the colours that you find around the edges of shadows when in sort of certain situations, and he kind of carries out a whole bunch of experiments, but just kind of ends up stopping pretty quickly. And he says this: when I made the foregoing observations, I designed to repeat most of them with more care and exactness, and to make some new ones for determining the manner how the rays of light are bent in their passage by bodies, for making the fringes of colours with the dark lines between them. But I was then interrupted and cannot now think of taking these things into further consideration. Since I have not finished this part of my design, I shall conclude with proposing only some queries in order to further the search to be made by others. Okay, so this is what happens, and then right, and so then there's a whole bunch of queries. There's 31 in the final book. Some of them are fairly innocuous, but some of them get quite metaphysical and crazy. So there's a widespread view that the queries of the optics were hypotheses. Here are a couple of the people who have made this kind of argument: Peter Anstey, Bernard Cohen, Alan Shapiro. They all make these kinds of claims. And so the question usually is, well, was Newton being disingenuous in his introduction of queries? Is he sort of trying to pull the wool over our eyes, trying to pretend that these aren't hypotheses? I don't think so. I think that Newton knew what he's doing. I think that he's not proposing them as hypotheses. He's putting them out there as queries. These are things to be kind of studied, investigated. Okay, so there's a couple of the queries. So there are things like this: do not bodies act upon light at a distance, and by their action bend its rays? And is not this action, ceteris paribus, strongest at the least distance? And so there's kind of a hypothesis in there, and he's trying to figure out a way of kind of being able to test this, how we're going to figure out whether this is really happening. Query 2, do not the rays which differ in refrangibility differ also in flexibility? Are they not by their different inflections separated from one another? So after separations, make the colours in the 3 fringes above described. In what manner are they inflected? So this is just a more general query. He's saying, how can we use this? How can we use the theory that I've already got to kind of explain what's going on in this case, and so on. I'm sort of running out of time, so I'm not sure. This is quite speculative too, so maybe I'll just kind of move on and, yeah?
No.
Oh, sorry. Yeah. Okay, so I think that there's something like this going on in the queries at the end of the optics, where kind of Newton is turning to his speculations, his hypotheses, and trying to think of ways of kind of turning these into fruitful empirical investigations in ways that might help him to explain the phenomena of light. And he kind of goes on in the last few, he kind of ends up trying to integrate kind of all the phenomena and things like that. I think there also might be this kind of interaction going on between them as well, where it takes a while to kind of get to a query that it can in fact be kind of experimentally tested, and so I think there's kind of some interplay between hypotheses and queries at that point as well. Okay, so some final remarks. Right, so we've seen that hypotheses have a bunch of different kinds of roles in supporting theory. They also seem to have a role where they feed through the queries. That one too. One that I didn't talk about here, but I think is going on in the Principia, is this one where hypothesis and theory are kind of in conjunction being used to kind of develop further theories and so on. But that's a bit more complicated. Okay, right, I'll just end with a final kind of comment about hypotheses. So, I, Bernard Cohen, in the introduction to the optics, says this: Newton's phrase "hypothesis non fingo" was never a guiding principle of his work. Well, on the contrary, I think my analysis suggests that actually this phrase was a crucial and enduring feature of Newton's methodology. I think he went to great lengths to try to extract hypotheses from the final versions of his theories, and I think he was kind of very careful in knowing and how he was using hypotheses through his work. Right, but of course, since this is a conference in honour of Howard Stein, let's let him have the last word on this. He says that a man of such imperious disposition never, into his most advanced age, made disproportionate claims about his contributions to science is one aspect of a tremendous discipline which he exerted, on the whole with remarkable success, in keeping the imagined parts of his vision distinct from the proved, the conjectures from the certainties. And that's all. Thank you.